Ladies and gentlemen, welcome to the second talk of this session. The speaker is Professor Mathias Schacht from University of Hamburg. He is a well-known specialist of graph theory and combinatorics, and he will talk about extremal problems in random discrete structures. Okay.
So can you hear me? Oh yeah, now I can hear myself also. I will talk about extremal problems in random discrete structures, and so on the first slide I put up some of the main people who really shaped these fields in both ways. So first of all, in the middle you can see Paul Erdős and Rainey, who both kind of are considered the inventors of random graphs, even though maybe these models were considered before. They were certainly the ones who first systematically studied them. And also Erdős, of course, was one of the main drivers of the field, which is now known as extremal graph theory or extremal combinatorics. And one of the main early results I will talk about is together with Stone, which you see here, and of course Turan, who also had one of the first main contributions to the field. So since I wasn't quite sure about the background, I will go fairly slow, and in the first part of the talk I give some overview about what maybe extremal graph theory is, or what is my personal perspective on extremal graph theory, and then I will move to the more advanced topics, okay? So that will be the plan. Okay, so what is extremal graph theory? So the way, in an abstract terms, one can state it like this. So we have a property, let's say P, and this could be some graph theoretic property, for example, not containing a cycle or not containing a clique on T vertices. And then we usually have a parameter. For example, in this talk, it will be mostly the number of edges, or we measure the size. And then, yeah, so the question is, in some sense, all what we want to do is some analysis over this set given this parameter, right? So we want to know what is the extremal set. Of course, in order to make this more precise, we should also maybe fix the vertex set so that these parameters are not infinite. But yeah, of course, we will do this in a couple minutes. So the typical question is, what are the maximal structures having this property? So what are the maximum KT-free graphs? How do they look like? And yeah, what can we say about them? Then other questions which are closely related are, for example, we are interested in how large is the property P itself, right? So meaning how many KT-free graphs, for example, are there on n vertices? There's also more refined questions like the number of maximal structures we would be interested in, or what is the typical structure with that property. So these are all more and more refined questions, and I would all consider them part of the framework of extremal graph theory. So today, as I said already, so the guiding example here in the beginning of the talk will be that we are clique-free. So in general, maybe we don't contain F as a subgraph, as a normal subgraph, we forbid F. So when I say F-free, I mean in the subgraph relation. And but yeah, so I think you don't lose anything if you essentially imagine all of the talk to be just F is a triangle, right, or a clique, kind of. Okay, so for that extremal type question, so the central definition is that of the extremal function. Where we make this more precise. So we want to know what is the maximum number of edges a graph H can have if it has n vertices. So this is maybe just an awkward way to write that H has n vertices, but it will be beneficial in a couple of minutes. And H doesn't contain a copy of F, and this we say is the extremal function for n and F. And this parameter is usually a little bit unpleasant to deal with because you easily run maybe in some divisibility issues and so on. So a rougher parameter is just, we scale it to the appropriate density. Okay, so since the graph obviously can have n choose 2 edges, it makes sense to divide this by n choose 2. And it's not so hard to show that this function is decreasing, and so the limit really exists. And this parameter we call the two-run density pi of f. Okay. So for graphs, this is fairly well known. So this kind of is maybe the first question which I put up on the first slide. We would like to know what is this parameter, and there's an answer due to the work Mantel, who solved it for the triangle, and then Turan, who proved it for the cliques, and Erdős and Stone for general f, that we can express this parameter in terms of another graph theoretical parameter. Of course, the question may arise, if you're not from graph theory, why we like this result, right? So, I mean, we put a graph theoretical parameter on the left, we have another one on the right, and maybe this is all what graph theory is about. Yeah, so there's maybe some people who would say that. I mean, there's certainly one advantage. So here we have a limiting process, and this is at least computable, right? Maybe not efficiently computable, but we can decide these densities and we can calculate them. Okay, and this is maybe so one of the cornerstones of founding blocks of extremal graph theory, and it's usually called the Erdős-Stone theorem, even though, I mean, one should also mention, so this connection with the chromatic number was first established in a paper by Erdős and Szymonowic and kind of gave the whole result a much more appeal and certainly had an influence on the field. There are also this precise parameter is known in some cases. For example, Turan did it in the clique case. And also if you are critical graphs, meaning that the number drops as soon as you remove an edge, you can extend these results. Let me mention that it's somehow somewhat mysterious, or kind of that this kind of result, which you would maybe teach in a graph theory course, so in half an hour, does not extend to hypergraphs. So for hypergraphs, as soon as we increase the uniformity from graphs to hypergraphs, even for 3 uniform, even for the most simple examples, almost nothing is known. Okay. Okay, so the second type of question, so now you can ask, if you know this Turan theorem, is in some sense the stability question. So how do the extremal examples look? So from Turan theorem, he already established that they are T-1 complete bipartite graph. So if you think about the triangles, the complete balanced bipartite graph would be the one which achieves this bound and is optimal, and you can show for the pure extremal question, this is a unique example. And the question one may ask is, so what about extremal graphs? How do they look like? What kind of structural properties we can say? And how does the almost extremal graphs look like? And this was answered by the work of Erdős and Szymonowic, who proved this beautiful stability theorem, which says that if you are close to the extremal number, so this is an assumption here up to an arrow of little o n squared edges, I mean small constant times n squared edges, then you can also, you are close to this extremal example. Okay, so in general, if you want to know how do the extremal graphs look like, they basically come just from the simple construction which we considered here, that you take a partition where the number of vertex classes is smaller than the chromatic number, so you cannot fit your graph f inside. And in some sense, all extremal examples are close to this construction. Right? So this is what this theorem says. So what does it tell us? So it tells us kind of this, or it answers this question, what is the structure of the almost extremal examples? Okay, and the next question which I put up there is kind of, you want to know how is a typical KT-free graph, how does it look like? Of course, this you can ask in more refined way. So, but in the simplest way, you say you have the set of all triangle-free graphs, you close your eyes, you pick one, how does it look like? And it's kind of course, easy to conjecture that maybe it's just kind of a subgraph of the complete bipartite graph. And this was indeed shown. So here I even put up the question one more time. In the general case, even for cliques, by the work of Colaitis, Premel, and Rothschild in '85, who showed that if you count the graphs which are T-1 colorable, and the graphs which are kt-free, that the ratio converges to 1 as n tends to infinity. This was an extension of for the triangle case, this was obtained earlier, a couple years before, 10 years before, due to Kleitman, Rothschild, and Erdős. And this result is kind of influential in more ways than it's kind of just a predecessor to that one. It also, we will talk, or in later parts of the talk, I will briefly touch on the development of the container method. And there was a series of papers in the 70s and 80s which you could say built up to this container method. And I would consider this a part of it, kind of, even though it's not so directly the connection, but it's certainly one which you could easily put in the build-up of it. Okay. Okay, so this is the short summary of extremal graph theory. If you want to know how many edges a kt-free graph has, you take Turan's theorem. If you want to know the precise structure, this was also answered by Turan in the case of cliques. If you want to know the approximate, almost extremal graph structure, then you go to the Erdős-Shimonovitz stability theorem, which gives you the answer to that. And the typical structure of kt-free graphs was resolved by Colaitis, Prömel, and Rothschild in the 80s. Yeah? So in some sense, this is kind of a nice, fairly complete picture for the clique case. Okay, so in some sense, if I would say, okay, so these are the questions we are interested in, then maybe everything was resolved by 85. So what is the rest of my talk about? So, the new aspects which were considered were systematically starting in the 90s is to which extent these results can be transferred or scaled to other sequences of graphs when you move away from the clique as a host graph. Okay, so now I use the clique in two different ways. Once it was forbidden, and once when I had this awkward H as a subgraph of Kn. And when I say moving away from clique being the host graph, I mean this H being a subgraph of Kn. Okay, so the question is, can we replace Kn by other graphs and still have similar type of results? So for that, we easily kind of extend this notion of the extremal function. Now it's not given by Kn. Here there was written n, which just indicated that we said H has n vertices. But now I just want that H is a subgraph of G and H is F3, and what is the extremal? What is the most number of edges such a graph H can have? And so we will, strictly speaking, we will consider sequences of graphs G, and in some abstract way, we could say we would be interested in which type of sequences have the property that we can transfer the earlier results. So for example, we would say the sequence has the Turan property. If this is true, the Turan density relative to the graph Gn is the same as it would be relative to Kn. So the Turan density scales appropriately. So let me make one concrete example. So as I told you, so by Mantel's theorem, the Turan density for the triangle is 1/2, meaning if I take more than half of all possible edges on n vertices, I will find a triangle. And here I would like to know the same thing. If I take more than half of the edges of a graph Gn, does it contain a triangle? And if this is true, then the sequence would have this property that it has the same type of Turan type behavior. Okay, and the first results which appeared in that direction for random graphs appeared in the work of Frankel and Rödel in the mid-80s. So here we consider the binomial random graph, G and P, where the edge probability is 1/√n. And they proved that for this edge probability, the Turan or the Mantel theorem scales in that sense, as we put it here. Okay? However, to be fair, they were not really interested in kind of maybe in this abstract framework. So at that time, of course, most of the or a large part of our field was driven by the questions of Erdős, and of course there was a question of Erdős which he asked concretely, which they tried to address, and I would like to tell you that question as a small detour. I should also mention that the general case for cliques, if you take constant edge probability, so for example 1/2, this was addressed in a paper by Baba, Shimonowitz, and Spencer in 1990. Okay, so what was the question Frankel and Rödel were really interested in at the time? So this is a question which arose at the first Poznan seminar on random graphs, which is maybe by now one of the main conferences in the field. This is, unfortunately, I couldn't find a better picture. So in the proceedings, they published this picture. So here you can guess that this could be Erdős. Here it's kind of important, this is Neschitral, and the question was posed by two of them. And you can see some other mathematicians from the time and guess them if you know what you are looking for. But let me not go into that. So the question Erdős and Neschitral asked, and at the conference, but it appeared in another paper by Erdős in the same year, was phrased like this. So at the Poznan, let me just read what he wrote. At the Poznan meeting, Neschitral and I conjectured that for every epsilon there's a graph which contains no K4, but every subgraph of density 1/2, relative density 1/2, because G has E edges, contains a triangle, right? So in some sense, they wanted to have a K4-free graph for which the Turan property or the Mantel property in this case scales appropriately. And then he writes, this conjecture was proved a few weeks ago by Frankel and Rödel using probabilistic arguments. Their graph has that many edges. So, I mean, the argument works for the slightly stronger bound which I claimed, but if you look at the paper, this will be the bound which they have. And we believe that the conjecture fails if you assume that the graph is dense. So this is what is written here. So if the number of edges would be constant times n squared, so this graph, of course, just has n to the 3/2 edges, but if it would be constant times n squared, then such a graph does not exist. Okay, so that was the question. So, and one could generalize this problem easily. So the question is there a graph which doesn't contain a clique of size kt plus 1, but whenever you take the Turan density proportion of its edges, then it contains a kt. And of course, I mean, this question only really makes sense if you think about a sequence of graphs, and kind of let's avoid this as a technicality here. Okay, so what the answer to it is, because the random graph at edge probability n to the 3/2 doesn't contain many K4s, you can easily get rid of them, and then you will still have this Mantel property, and this kind of answers the question. So this is how you prove the positive result. And actually you can prove this positive result really by an application of Goodman counting, which can be transferred to that point of the edge probability. So this is not very hard. So with some preparation, maybe one can easily give it as an exercise in the random graphs course. But so I would like to use, I mean, so to give you some proof, I would like to prove it to you the negative result, because it's also interesting. Okay. So yeah, maybe I should have mentioned this. So maybe it looks a little bit arbitrary. Why did Neschitral and Erdős ask this question? Well, so it has a kind of a natural analog to a Ramsey type question, which was proposed by Heinel and was solved in the first non-trivial or kind of very interesting case by Vogtmann. Which is the following. So can you have a Ramsey graph which has a Ramsey property for the clique but doesn't contain a larger clique? And in some sense, this would be an extremal analog of this type of reasoning. Okay, so they answered it, yes, as I already said, but they have to be sparse. So how to prove it, the negative result, right? So this I already said. So how to prove such a thing? So basically, the sketch of the proof is as follows. So you consider a graph of density D for some constant D. And now you know that every triangle free subgraph, or the largest triangle free subgraph, has at most half of its edges. So what this basically means that there's no balance cut, which has more edges than it's supposed to have. Because that would obviously violate, this would be a denser graph which would be triangle free, and the assumption is if you are above density 1/2, you have a triangle. So these balance cuts are triangle free, so they cannot be too dense themselves. And that implies that G contains a quasi-random subgraph. So I indicate with this longer implication arrow that this takes some more time to argue, and I will do this on the next slide. But if you contain a quasi-random subgraph, you contain cliques of all sizes. So in particular, you contain a K4, and that would violate the assumption, right? Okay, and the proof is kind of nice. One can explain it in pictures easily. So if you are not quasi-random, then you will have a subset of size half of the vertices where you have a loss in density. I mean, you could also have one which is already denser, but this is even an easier case. Okay? So let's assume you have half of the vertices and the density dropped to d minus delta. Now, you can look at the complement, and since you know the density in the middle is very precise, so you have to play a little bit with the constant. So let's say it's very precise, it's really density d here, because all the cuts have density d. Balanced cuts have density d. It means the graph has to make up its density somewhere, so this part must be denser. And of course, when you make this argument precise, maybe you will not hold the same delta, but kind of 0.99 times delta. Okay, and now you can apply the assumption of the theorem to this side. So either there you already contain a K4, because you will say D is, let's say, the largest D for which the theorem fails. So now we have some larger D, we have D plus delta. So here it's true. So that means there must be a cut which is excessive in the sense it really has more edges than it should have. And so this is just kind of, you have to a little bit fiddle with the constant to make this precise, but just for understanding the idea, kind of this is a valid step which can be easily fixed. And now it's simple, you just take a random partition of the right-hand side. You will keep the density d minus delta in between, and you will also keep the density d, which was here, across. So this is just a very basic hypergeometric argument. And that means that this by partition suddenly has too many edges because the blue ones and the black ones, they are the d proportion. But we had this gain, which we didn't lose here. And that's the end of the story. But yeah, so it's kind of a nice argument how to play with these densities and bringing quasi-randomness in the picture from this cut property. Yeah, so this is important. Otherwise, it's so it fails for constant densities. So for sparse graphs, you can find an example always as soon as you are at the two densities. Otherwise, the quasi-randomness would maybe not necessarily give you cliques. This is essentially what fails. Okay. So yeah, so what is so special about this n to the minus 1/2? So basically, and this is why then this deletion works, is it is a point where the expected number of triangles in the random graph and the expected number of edges coincide in the asymptotics. Okay, so before that point, when p is smaller, you have fewer triangles than edges. And that makes it easy to find a subgraph which has 99% of the edges without any triangles, because you just remove from every triangle one. But above this point, you expect every edge to be at least in a constant number of triangles, and then it gets more and more and more. And this is the critical point here, where the behavior of the random graph with respect of these properties, or extremal properties with respect to the triangle changes. So, yeah, so this is what I already said. Before, you can just delete an edge from every triangle, and you get this, which obviously violates because you just want to get here 1/2. And this leads easily to the definition of kind of the so-called, to investigate this parameter. Of course, in random graphs, this expectation, this basic expectation sometimes can be misleading because there could be hidden denser subgraphs in a graph F. So you have to maximize it over all subgraphs, and this is basically what this function does. So this secures you that if you look at n to the minus 1 over this parameter, that you have at least as many copies of any subgraph as you have edges. Okay, and this is kind of just the adjustment. And so in the 90s, so this was investigated and started, so people started a little bit look at these problems a little bit more systematically. So, and it led to a series of papers by various, or basically by subsets of these 4 authors. And in some of these papers, I mean, so this is a real human, it's Yoshi Koakawa. So this is Penny Hexel, which doesn't appear here in the name. So this is Yoshi Koakawa by a picture which he put himself on the webpage, so I think I'm okay to use it. This is Tomasz Wuczak and Wojtek Röhle. So they wrote a series of papers in varying subsets where conjectures of this form were put forward. In the end, it became known as the Koakawa-Wuczak-Röhle or KLR conjecture. But if you, especially this version, actually already appeared also in a paper by Penny and Tomasz. So I at least wanted to bring her into the picture. Okay, so and this conjecture basically said that if you want to know the threshold when the Turan theorem scales in the appropriate way, is given by this heuristic which we have just seen. And there were some attempts to work on this conjecture. And so before 2010, so as I said, so in the 90s, it was solved by, for cycles, this was addressed by work of Hexel, Koakawa, and Wuczak. And there were the small Klee cases, so the triangle case was done by Frankel and Röhle. And the K4 case, which really maybe was the first or one of the main driving papers in that area, was done by Koakawa, Wuczak, and Röhle, and that's where the kind of also variants of this conjecture were phrased. And then in the early 2000s, there was a group at ETH Zurich led by Angelika Steger, and they could solve the case k equal to 5 and k equal to 6. However, it seemed out of reach to extend this approach because somehow what happened is the approach was very much driven by embedding a clique by going through the neighborhoods. But at the threshold which you pick up here, the neighborhoods will get empty fairly quickly, basically after you reached half of t over 2. So now for small t over 2 and t are not so far away from each other, so you can overcome this barrier. But for large t, it grew and grew, and this paper became more and more longer and technical. And then, so it's eventually it was proved for all graphs, and this is so maybe what I want to report here. So this happened in between 2010 and 2015, independently by David and Tim Gowers and by myself. We kind of could solve this conjecture, and I will talk about this a little bit more in a couple of minutes. It also kind of then easily in the same way as I said before in the triangle case, it solves this general Erdős-Neschetl problem because this parameter of this density parameter is strictly larger for larger cliques, and that's kind of then you can easily apply the same deletion argument. Okay, so what does it tell us? So it tells us that this Turan's theorem, in some sense, or a weak version of Turan's theorem, it could be transferred. So if you're just interested in the Turan density, then this is established by this result. And there were also questions which are more precise, right? So for example, when is the maximal KT-free subgraph of GNP itself t minus 1 partite? So for the triangle case, so if you take the largest triangle-free subgraph of GNP, is it bipartite or is it not bipartite? And this was addressed for larger parameters of P in the early work of Babay, Spencer, Szymonowicz, and Spencer, and then by Breitel, Panagiotto, and Steger, already for P which tends to 0, with n tending to infinity, but it was resolved by DeMarco and Kahn. And you will see, so essentially it's the same threshold, but there's a logarithmic or polylogarithmic factor. And I could write here the formula, but I just didn't want to do it. So basically, the argument for it is as follows. So as I told you, at the 2-density threshold, you essentially have the same number of copies as you have this number of edges. If you want to have such a precise result, you really need that every edge is in a triangle, every edge is in a clique. And for that, you need this kind of essentially the same heuristic as in the coupon collector problem. So you need, in the expectation at teeth, a log n factor more, and that gives precisely to this polynomial. Okay. If you are happy with an approximate partiteness, then this can be done much easier. And in fact, this is the first step they use in that theorem. And this would also follow from this other work, which I mentioned. For the typical structure, let me quickly go over it. I mean, first, stability, this follows essentially by the same approach. When you do the Turan, when you transfer the Turan property, you usually get stability. In the paper by Conlon and Gowers, it's explicit. And my method were refined by Wojtek Samoti, and he showed that this can be done. More interesting is actually the typical structure of a KT-free graph. Because, I mean, one thing which is a little bit unsatisfactory in the colitis Permel-Rothschild result is that all these graphs are dense, right? And these kind of the subgraphs of the complete bipartite graph completely dominate the counting. And so maybe you want to have it more refined, scaled with the number of edges. And this was investigated for the triangle by Ostos, Permel, and Tara. And it was proved, or kind of the right generalization of this was proved by Balogh, Morris, Samoti, and Warnke in 2016 using this container method, which I already briefly mentioned before. Okay, so let me summarize what we've learned so far. So basically, the 4 questions which I put up in the classical extremal context, I think they now have sufficiently precise counterparts in the random world by that the threshold for GNP were established, and you can really transfer them to the other side. So now the question is, so what really happened after 2010 and kind of why this was kind of, before it was usually very case sensitive that you could only do it for K4 and then you had to do a lot of additional work to move to K5. So, one approach which was proposed already in the 90s was that one would like to transfer Semiramis regularity lemma to subgraphs of GNP. And then several of the results which I mentioned would be easily transferred. However, what we did in these approaches, I mean, what David did with Gowers and myself, we rather focused on the consequences and didn't really go after this regularity method. And for that, David and Gowers, they invented something which is now known or called the transference principle. And I'm guessing, I'm sure David will talk about it on Thursday. My approach was completely different, in some sense much more elementary, by a multi-round exposure of the random graph. But in subsequent work, there were 2 groups of authors who developed the so-called container method for independent sets and hypergraphs. So basically, we will get to it in a couple minutes. So all these results can be phrased in some abstract setting. And in that setting, all what you want to analyze is independent sets in hypergraphs. And for that, the container method was developed by Balogh, Morris, and Samoti, and by Saxon and Thomason in about 10 years ago. And this kind of allowed really to even refine the work and get these more precise questions, which I mentioned. What is good about these abstract approaches is that it's first of all, you can kind of transfer a wide range of properties, but not only for GNP, but also for other binomial random models. So you can consider random hypergraphs, kind of. So there you even you don't know the Turan density, but you can transfer it to the optimal threshold. or you can consider a subset of the integers, and I will tell you in a second. Also, I didn't mention it, but kind of these approaches also usually or were flexible enough to do the same, not only for extremal properties, but also for Ramsey-like properties. So let me briefly tell you some other extremal type questions which have a completely different flavor. So maybe one of the prime examples is Semeradi theorem, where you are interested in the maximum number of integers between 1 and n which don't contain an arithmetic progression of length k. So this was this question or this function was first put forward by Erdős and Turan in 1936. And they asked the question whether this function grows as a function little o of n, what is the asymptotics? And this was proved by Semeradi in full generality in 1975. There was earlier work by Ross and by Semeradi himself. And what I wanted to take, or what I want you to take away from here, that in some sense this is also an extremal question, right? So because you just want to know what is the largest density that you which a set of integers can have, which doesn't contain an arithmetic progression. So instead of forbidding a clique, you forbid an arithmetic progression. And in some sense here, you are even in a degenerate case because already positive density is sufficient. Okay, so there are multidimensional versions of it, and just so to show you a picture, so the multidimensional version would say, okay, if you, which was first proved by Fürstenberg and Katznelson, that if you take a positive density subset, which is here indicated by these red dots, then within that you find, for example, a regular set. In that sense, you find a two-dimensional grid kind of size, of fixed size. And of course, because I drew the picture correctly, so here it is. Another kind of easy extremal result which we could phrase is so-called sum-free. I mean, we already a little bit talked about, or we talked about such things. So for example, you want to know at which point you have a solution to the equation x plus y is equal to z, right? So which subsets of the first n integers. And then one can easily show that as soon as you have n over you take half of the integers, then you will have such a solution. Before you don't have it because you could take the odd numbers, or you just take the second half of the interval if you just take the first n integers. But if you have one more, then you will have a solution. So I mean, corollary is kind of, I mean, a weakening of this result in the density terms would be, okay, so if you have density strictly larger than 1/2, in a finite, in a subset of the first n integers, then you have a sure triple, meaning you have a solution to this, and you can even insist that x and y are different. Okay, so the general framework is the following, that the basic extremal question is, at which sufficient density you have the interesting substructure. And if you want to abstractly capture all of these properties with one definition, then you could kind of try to phrase it in this abstract notion of hypergraphs. So basically you will say a hypergraph has the alpha dense property if the following is true: whenever you take a subset of the vertices, which is alpha proportion, then you have an edge. Okay, so this would be the short version of it. Of course, there are some more letters floating around here, so you want to have density slightly larger than this alpha. And I'm not only happy with one edge, but I want to have a constant proportion of all edges. So this we would phrase under the term of supersaturation. Okay? So, and this way, of course, I can phrase all the results which we have, or the basic extremal results which we have seen so far. So for example, so if you want to encode Turan's theorem like this, then the vertex set is just the edges of the complete graph. And the edges would be the edge sets which form a copy of the clique or the copy of the graph F you are interested in. Okay. But these hypergraphs will be fairly sparse, so that's maybe one thing one should keep in mind, and that maybe makes it a little bit difficult. But then Turan's theorem would tell you, if you take a subset of the vertices of this hypergraph, it just means you take a subgraph of a given density, let's say, of the density of the Turan density, then inside you find an edge, and it's even true by the supersaturation phenomenon that you find a full constant number of all possible copies. If you're interested in Schur's theorem, which would be here explicit, so then the vertex set would be just the first n integers, and you would put in a triple whenever you have a Schur triple, so you have a solution to the equation x plus y is equal to z. So this would be a 3 uniform hypergraph on n vertices, but the number of triples you would have would be only constant times n squared. And of course, you can do the same with Semirady's theorem. It would be, in some sense, a degenerate case because already positive density would be enough. Your hypergraph would be, again, the integers 1 to n, and the edges would be the k-term arithmetic. And what is a little bit surprising is that, I mean, I think it's fair to say that these theorems are considered fairly different in the deterministic context, meaning that maybe Schur's theorem is really easy exercise. Turan's theorem is also not very hard to prove. But Semirady's theorem is considered one of the prime examples in additive combinatorics and one of the major theorems in the area where no really simple proof is known. However, for the transference to the random setup, as kind of the work of David and Tim Gowers showed, and my work showed, you can all treat them the same way. And that was maybe a little bit surprising at the time, because before one really tried to work for one property, and maybe one would have expected fairly different proofs for transferring Semirady's theorem and transferring Turan's theorem to the random setup. Okay, so maybe I should a little bit speed up. So the relative version is basically, I already mentioned it, so we are interested in random subsets. And so this would be a concrete instance like in Semirady's theorem. So let's make it explicit. So you fix k and delta, and you fix a random subset x, and you want to know that this random subset asymptotically almost surely has the property that if you take a relative dense subset, so now you take so the random subset has the property that for every subset, which has relative positive density, so you scale it, of course, to x, then it must contain an arithmetic progression of length k. Okay, so this is kind of the game we are playing. And similarly, if you want to transfer Turan's theorem even for hypergraphs or for graphs, you want to take that the random graph or random hypergraph asymptotically almost surely has a property. If you take a subgraph which relatively has the proportion of edges as the Turan density tells you, a little bit larger, then we'll find a copy of f as before, where you just had here kn, right? Okay. And so what we were interested in, what are the asymptotics? So these properties are not strictly monotone, but they are essentially monotone, so it makes sense to ask for the threshold. And so basically, so this was the type of question we asked, and this would be the type of question if you would ask it in this abstract setting. But now this would just make it precise what I just said. So for the lower bounds, we already a little bit have seen them, but let me just remind them. Of course, the first simple idea would be that, of course, for the random subset to have even the stronger Semirady property, it must contain arithmetic progression on its own. And this would give you kind of a lower bound of this type. However, you can be a little bit smarter, and you can say what we already did, that when we thought about triangles, we said maybe we want at least as many triangles as we have edges, otherwise we remove an edge from every triangle. And in all instances which I told you, we could do such a trick. Okay? And this gives rise to the following heuristics. So for example, for Schur's theorem, that you would like that the expected number of Schur triples, which is on the left, should be at least of the size of the set, the random subset of the integers. So basically this tells you that P should be of the order 1 over root n. Similarly, for Semirady's theorem, you get a heuristic like this. And for Turan's theorem, you get this which defines this parameter m of f before. So you would get the minus 1 over mf. And yeah, so in a nutshell, so what the result said is that this lower bound is asymptotically correct. So this idea of getting to the threshold is correct, and of course the hard work was to establish that this is true. So if you spell out all technicalities, how such a theorem looks, it would look like this. Of course, you have a little bit to think about which property you're really transferring. So, and the point which I want to make here is that the delta is fixed for a moment because it will have an influence on this constant c. Okay, but maybe it's this may be a little bit too much. As I said, so this general result kind of allowed the transference in this more abstract hypergraph setting under some assumptions. And but then one could prove transference for all these properties at the same time. So let me just briefly make a few remarks what the stronger version of the theorem tells you. So first of all, it tells you that the supersaturation property is also transferred. So you not only find one copy of the graph f or of the arithmetic progression, but you find a constant fraction of the expectation, which is kind of encoded in this quantity. The second thing is you can start slightly different. So you can pick deterministically an arbitrary subset of the vertex set of this hypergraph, which has a given size. And then you have to adjust, of course, how much you have to pick out inside of the random subsets induced on that set. Okay, and if you think about it for a minute, you will see that this is the right dependency of the parameters here. And this works, and in fact, this was important in the proof to set up some inductive argument. This is maybe a slight advantage of this, the approach which I had is that the error probability for this one statement was exponentially small, so which is in some sense up to the constant optimal. And yeah, so kind of roughly speaking, what this result tells you, if you have an extremal property which supersaturates, which of course not all of them do, then you can transfer them to the binomial random model with exponentially small error probability. Okay, so let me conclude my talk with a few mentioning of some related work and open questions. So, so the threshold which I showed you, or which briefly showed you on the slides, they were so-called maybe semi-sharp thresholds. So it's not only that we have the asymptotics, but we can show that that they are just a constant factor away for the 0 and for the 1 statement. And of course, it would be interesting to decide whether these thresholds are even sharp in the sense that the scaling window is smaller than the threshold itself. For Ramsey properties, this could be done to a certain extent via Friedgood's criteria. But Friedgood's work really requires the properties to be monotone, and that we don't have here. Another question is to which extent these results can be transferred to more complicated subsets, for example, to pseudo-random subsets. So even for arithmetic progression of length 3, this is kind of an interesting open question. So basically the question is, of course, how you measure the pseudo-randomness. Well, you could look at the Fourier coefficients, and if the second largest Fourier coefficient, absolute value, smaller than this, then maybe you would like to already transfer the property for arithmetic progression of length 3 at that point. And this is open, and maybe there are also contradictory beliefs whether this is possible or not. So currently the best lower bound is of this form, upper bound, which is more strict than maybe what could be true. And similarly for pseudo-random graphs, there's some well-known concepts for sparse pseudo-random graphs, ND lambda graphs, or graphs where you measure somehow deterministically uniform edge distribution. And there are also most of the problems open because we don't really know good lower bound construction. So maybe this is the main problem in that direction. And having said that, I thank you for your attention.
Thank you for this beautiful talk. Is there any question?
Can you comment on how much of these problems or the methods can be applied to the degenerate case where F is bipartite?
Yeah, so this is of course a very good question. So you would like to know a more precise answers, for example, if you forbid even cycles, right? And so this is, there was a lot of work done in these original papers by Penny, Yoshi, and Tomasz already in the 90s. And there are some approaches also, maybe if you think, for example, in the direction of transferring removal lemma and things like this. So David and Benny have a paper on this, how far you can go, but usually you need some additional assumptions. So this is so these methods break down fairly quickly when you want to do it. So you will need some more precise estimates.
Another question? Okay, let's thank the speaker again.